Welcome students to again a movie about data science. Today we're going to talk about classification. It's a supervised method, and more specifically we're going to cover KNN. So first content of the total lecture, but we will divide the pieces of this lecture up in smaller movies. So it's about classification. What you see here is a dog and a horse, and we want to know, is it a dog or a horse? So we'll cover what is classification, what we as humans do. We're gonna discuss KNN, that's the main topic of this movie. We're gonna talk a little bit about how you prepare your data, how you validate and test it, and performance metrics. How good is your model? How good is your prediction? And we'll go in a little bit more detail in KNN. In the next movie we will discuss a little bit more about decision trees. The movie thereafter will talk about naive Bayes classifiers, and finally support vector machines. So first, what is classification? It's based on features and it predicts labels. So it doesn't predict numbers, but it predicts labels. So what you see here, and it's the same case, it's the horse and the dog. We've got features, we've got the height on the left axis, and we've got the weight on the right axis. And if we plot from a lot of different dogs and horses the data, we see that we get this graph. And the label we have for each data point is the dog or is the horse. And our target is basically, if we've got a new data point, is the horse or is the dog? Well, this data point is pretty close to the red one, so we assume it's a horse. This data point is pretty close to the blue one, so we assume it's a dog, and this one is a little bit more exciting. So where do we apply this? Well, I will show you later on a little bit more, but you could apply this, for instance, to recognize which digit was written. So you could use it for handwriting recognition. You could use it for disease detection. Does a person with certain symptoms have a disease or not? Spam filters. Is a certain email spam? Credit ratings. Should a certain person be granted a loan or not? Wine quality. Is a certain wine good? What rating out of a few options will it get? So which label will it get? So what are the steps for setting up a prediction algorithm? Well, first we need to have the training data. And the training data, because we are doing classification and supervised classification, we need some features, that's normally labeled X, and we need a label, and that's normally labeled Y. So in the case of the dog and the horse, we got the features height and weight, and apparently this line, this row, with the height 2.3 and weight 213 is a dog, and this one is a horse. So this is the data with which we train the model. And basically we train the model, and after we have trained the model, then we want to input a new data point and see what is the most likely label Y. So if we got something like 3 kilogram and weight 3 feet high and weight 200 lbs, then we would assume it's a dog. So how do we do this as humans? Well, we do basically visually. We saw already in the first example, if we've got here a new data point, like something here, well, you're gonna look, well, this is pretty close. I'm assuming it's the red dot, which was the horse. And what you basically do visually in your mind, you kind of divide this up in regions. Like, well, this seems all to be horses, and this is mostly dogs. And that process we want to mimic with the computer. So basically, we want to make a model which predicts, if we put in a new data point, what is the most expected label? Well, the one which is the main topic of this talk is the KNN algorithm. And what it basically does is it looks at the data point and it sees what are my nearest neighbor. That's also the name. So when you look at this star, you see that there's one neighbor of class A and two of class B. And if we've got a k is 3, so we've got a 3 nearest neighbor algorithm, then we say we take the 3 nearest points and see what the majority is. And you see already, well, in this case we would predict it to be the purple class. Okay, that's good. You can also change that k value, so look at the 6th nearest neighbor, or look at the 5 nearest neighbor, or just look at the nearest neighbor. And we'll talk a little bit more about that later on. So how do we need to do that? Well, we need to calculate the nearest distance and then see the distance from this star to all the other points, and then basically just find the nearest one. And that's it. So I've also added here a link, I believe, for a very simple demo. In the rest of this talk we will always show it with 2 features, but that doesn't have to be. You could also do it with 3 features, for instance, or you could do it with, and 3 is still visually pretty easy to visualize, but you could do it with 4 features. It's a little bit difficult to imagine how we would display that in a plane, but when you look at the math, well, 2, 3 or 4 dimension doesn't really matter for the math. For the math you can still calculate the distance. We will show later on a little bit more about how you can do that. So you could even, let's say, I told you already that I was going to come back to this example for this handwritten digit. So we can use the KNN algorithm for the handwritten digit. But the first choice is then, what kind of a feature do you take? Well, I'm going to show you an example where they took a really simple feature. They took basically the gray value of each point, and it's a 28 by 28 like matrix or field, and basically they took each point, each gray value of each point here, as a feature. And that means that you get a 784 different feature for each digit. So instead of 2 or 3 dimensions, we get a 784 dimensional thing, where with the nearest neighbor algorithm we want to know what is the shortest distance. Well, visualizing again is very difficult. A 784 dimensional space, but in math it's actually quite easy. And it doesn't really matter if it's 3, 4 or 5 dimensions. I'm just going to show you where they work out this example. It's really nice. But for now, just keep in mind that I'm going to show you for visual, to make it visually easier to understand, only with 2 axes. But those 2 axes can actually be 100 axes or 5 or 3 or whatever you choose. Okay, going back. Well, we applied the KNN algorithm for our horse and dog problem, and you see that the amount of neighbors you choose, it has a pretty big impact on how this field, basically, this is the horse field, this is the dog field, how this field develops. If you've got a smaller one, you see that this small red horse is really important still, and here, well, we're just gonna ignore the small horse here. Okay. And if we go to larger case, we see that that jagged line is gonna be more smooth. Well, which result is better? You can discuss a little bit about it, but uh, uh, well, pros and cons, right? I think this is, well, not so nice, to be honest. This is maybe a little bit nicer, so I don't know. Pros and cons. What you see at this example is a phenomenon what we call overfitting. And basically, overfitting means that your algorithm is so fine-tuned that your training data to your training data that it doesn't generalize that good. So if you've got new data, it really it's not so good in making a general prediction. It's gonna do exactly what your training data said it should be, and it doesn't generalize so good. It's not a smooth boundary, but it's a very jagged one, which maybe is not so bad in some cases, but like, well, on this you can say, well, this may be okay, but here you can really see, well, I think this is a little bit overfitting, right? So, and the problem is that if you've just put in new points, it can be lead to false results. What you could do to work around this, and we're gonna show that also, just make the k bigger. By definition, then your boundary will get more smooth. But you can also vary it and just see what is my optimum setting. So basically, back to KNN. We've got some things to choose. We need to choose the k, not too low, then we get overfitting, and not too high, because then we really lose resolution. And we need to choose a distance matrix. So how are we going to measure the distance between points? So the simplest distance matrix is basically just Pythagoras. What you see here, if you've got a new point, then basically what we're doing is this distance is, let's see, that's the weight, so that's this part. This distance is the height, so that's this part. And what we're basically going to do is just use Pythagoras to calculate this distance. You can generalize this to 3 dimensions. The only thing what happens is that you get here an extra term, but also to 4 or 5 or 6 or 784 dimensions. The only thing what happens is that you get here extra terms for each dimension which you add. So this works. This is actually good. There is one issue, and I've made a small demo of this effect. When you look at these data points, these red ones and the blue ones, well, and we want to estimate where this green belongs to, then we would say this belongs to the red ones, right? Visually, we as a human would say this belongs to the red ones. But if we do the math, we have to look at the scale also. If we do the math, we will see that this scale is actually much larger than this scale. And the result of that is that this distance is this axis is made more important than this axis, which you don't want. So basically, when you look at this distance, this is between 70 and 120. So that's around 50, because this distance is almost nothing. Or this distance and this distance, which is much more. So when we would use it, it would say it belongs to this class. And well, visually you can see that's maybe not the result we want. The solution for this is scaling. So basically what we did here is scale this axis, that always the range of these values is similar for this axis and this axis. And when we then apply again the KNN algorithm, we will see that it predicts that this one should be here. Again, I made a demo of this, including the code in this YouTube link. So that scaling is an important part of that preparing data. So let's look a little bit at the whole procedure. First we normalize, we scale the data. One way to do this is find the mean and the standard deviation of the data and then normalize the feature according to this formula. So what you're basically doing is you subtract the mean from that value. So then you get basically the deviation versus the mean, and then you divide by the standard deviation, and that means basically that you normalize the distance. And then you get a new data point. And then we use Pythagoras. And again, what I told you already before, but here you see the whole formula. If you've got a multidimensional axis, it looks something like this. So this is for 2 dimensions. If you've got more, then you just add these terms. That pre-scaling or that scaling can be done by automatically by Python. That's really nice. So let's say we start with the data from X with Y labels. We import the scalar from sklearn. We make an instance of the scalar. So basically this is like the template, and now we've got an object or an instance of that template. And then we fit the scalar to that data. Scalar fit to the data. So I said X, but it's actually X raw. And then we transform that data using the scalar, which was fitted with this action. And then we get a new scaled data, and that data we can use. Here we can visualize it a little bit. Okay. Another way to do this a little bit different, the distance metric and the scaling, etc., is using Mahalanobis, but I'm gonna skip it for now. We'll have a look at it later on in the course. So basically what we're gonna do, we're gonna prepare the data set, transforming feature, and this is what I'm gonna explain is generally what you do for all training of all models. So this is not specific to KNN, this is for everything where you want to do recognition, basically, where you want to do classification. And basically you're splitting up your data set. You're gonna split it up in a training set, a validation set, and a test set. And the percentage you see roughly here. So the training set is the big part of your data, but you have a smaller validation set and a smaller test set. And if you pick a model and you train it, so it's could be KNN, but could be every model, doesn't matter. You train the data on the training set. You fine-tune parameters. For instance, what is the best value for K? Should it be 1 or 3 or 50 or whatever? You train it using the validation set. So this thing is iterative. And you can also use this to try different models, etc. Lastly, you're gonna evaluate the performance. And this one, it's pretty tricky. You can do it only once. You evaluate the performance on the test set. Once you've used this test set, then basically you cannot use it anymore. It's gone. And the reason why, if you optimize it for the test set, basically you're replacing then your validation set with the test set. And with this last step, you want to see how good did my model generalize for totally new data points. And if you do this last test iteratively, well, you're not testing your generalization, right? You're just overfitting again, but now for your test set, which is not what you meant to do. So you can use this test set only once, and that's it. So this is the procedure, and this is really quite important, and this is really something you need to know going on, the difference between the training set, the validation set, and the test set. It's quite important. There's another option, cross-validation. In this case, again, we divide it up in training data, validation, and test data. But we split that training data up again in more blocks. And basically, we split it up in a fold. What we're basically doing is each part of that training data we're going to divide up in, for instance, 5 different blocks approximately. And for the first test, we're going to use this one as a validation set. And for the second test, we're going to use this one as a validation set. And for the third one, we're going to use this one as a validation set. The fourth one, this one is a validation set. So then we can do this parameters, the fine tuning of the parameters, we can do with different types of training data, which is nice. And what we then can do is take the average result to determine the optimal parameters. Okay. So this splitting of the data, can we do this automatically? Yes, we can. It's Python after all, so a lot of things can be automized. We'll basically import train test split from sklearn again, and then we can split the data set. And of course, we need to do the X we have to split, but also the labels we have to split, right? We need to split both. And then you can split it in a train and a test set, and for instance, those test set we could split again, and then we get a validation set. So we get the training set, validation set, and the test set. Okay. So how can we test if a if a algorithm is good in classifying? How can we quantify that? How can we put a number it? So we start by running it on a fresh test set, but then how good is it? Well, a very easy way is using the confusion matrix. A confusion matrix compares predicted results with actual results. So here you see that the actual class, there were 5 in the actual class horse plus 3. So there were 8 in the actual class horse, and there were 5 in the actual class dogs. When you look at it, you see that he predicted of those 8, 5 correctly as being horses. So this is good. And when you look at the dogs, you see that it predicted 3 dogs actually as being dogs. So that's good. Those three and those 2, that's not so good. It was a horse and he thought it was a dog. It was a dog and he thought it was a horse. So that's not so good. Okay. So how do we label this? Well, when it should be in case of medical diagnosis, and then it's a little bit different there. It's not like it's a dog or a horse. No, it's more like, are you sick or not? Or are you contaminated or are you not? So the true condition in that case can be condition positive or condition negative. And the predicted condition can again be positive or negative. And then you see we've got true positive. So yes, I'm sick, and yes, the test predicted correctly. And it can be condition negative, no, I'm not sick, and also the tests say the same. And you can have false positive and false negative. Well, just a small intermezzo, a nice test, because this seems pretty simple and etc., but it can be a little bit nasty in practice. So let's say we've got all the U students, 10,000 people are struck by an alien virus. And 1% of the people are infected. Okay. And let's say that we have a test available and we know the reliability figures of those tests. And that test is actually pretty good. So it only gives 1% false positives and 1% false negatives, which is really, really good for those kind of tests. Well, it's an alien virus, so it's amazingly good. But even for a normal virus, it's very good, not bad. And you take the test, you are a student, and you take the test and it's positive. But what is the chance that you are really infected? And I go a little bit slower here, let you think about it. Because your first idea would maybe would say, well, if I'm tested, I'm positive, but there's 1% false positive, so the chance is 99% that I'm really positive. That's maybe your gut feeling. But it's very wrong actually, and I'm gonna show you why. So let's say we test those 10,000 students, and 100 of them are sick and 9,900 are healthy, because 1% of the people were infected, right? So we've got 100 sick, 9,900 healthy. If we test those 100 sick, it's 99 positive, 1 negative. Yeah, okay. Sorry. Of those healthy we test a lot of them are negative. 9,801 are negative, no problem. But there's also 99 positive, again, because of those here, the false negatives. Is that true what I'm saying? Yeah, I think so. No, this is the false positive and this is the false negative. I said it vice versa. Okay, but the idea is the same. So when we look at this, of those 10,000 students, there were tested 99 positives, which were really sick, and 99 positives, which were really healthy. So that means if you are tested, what is the chance then that you are really infected? It's only 50%. And this is kind of mind-boggling, but it's true. And it's also one of the reasons why the testing with COVID was quite challenging. Because even if your test is really good, then you still have this effect, which can lead to a lot of false positives. And you need to handle that. So, it was a little bit intermezzo, but I think this part is really interesting. And it also says something about how good is your when you make a model with data science, etc., and it has a very high percentage of being good, or very low false positive rate or very false negative rate, it could still be that for your application, or the 1% is still way too high, way not acceptable. So this is something where you really have to think about, where do I apply this? If I apply this, for instance, to identify murderers in a population, you've got some kind of data science, and you execute a murderer if your program says uh, you're a murderer, because the amount of murderers in a society is so low, then that 1% false positives will lead to a lot of unnecessary deaths. So those, what is good enough actually depends very much on your application. So the confusion matrix, yeah, some more numbers. We can look at this, well, basically it's definitions. So we can look at the accuracy, and this is basically the part which is predicted correctly versus the total. So in the previous case we saw that I think like 99% of the corrections were correctly, so the accuracy would be something like 99%. The recall, that's basically the part, so true positive plus false negative. So those are all the people who are sick, and what ratio of those people who are sick did we really find? So that's the R. That's basically how much sick people did we find from all the sick people. And the precision, and again this is all based on that false negative, false positive, true negative matrix which we had before. The precision is the part of the people we marked sick that actually is sick. So that's the true positive plus the false positive. So these are the people we said were sick, but this part is only sick. Okay. So that R and the P is really important. In basically you want to have both at a certain value, and what a lot of times is used also is the F1 score. It trades off recall and precision. I'll show you a little bit later on. It's the harmonic mean of the two. Well, this formula I'm gonna show a little bit more. This is the formula. And I'm gonna take the analogy with resistance. These are two resistors in parallel. When we calculate the total resistance, we see here that this is the formula for this. And you see that it's very close to this. It's the same except for the two. When we look at this resistor network, you can see that if this resistance is very low, it dominates. If this resistance is very low, it dominates. So basically this formula determines that if one of them is very low, then the total resistance of the thing is very, if this one is very low, it's very, the total resistance very close to that, to this resistance. When we look at this F1, this means, with this formula, it means that the lowest one, which is the worst, right? Because the P and the R needs to be high, the worst dominates the score, which is nice. So the F1 is actually a way to take the recall and precision together, but still have them weighted. Like if one of them is really bad and the other is really good, then it's still very bad. If they're equally bad, then that's the nicest outcome. And basically it serves as a good trade-off between the two. And you can still do a little bit manual tweaking. There's a lot more things you can determine with all those, or a lot more definitions you can do, like true positive rate, recall sensitivity, false positive rate, blah 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 blah. Our F1 score is here in the corner. I'm not gonna explain them all. It's basically a different way to adding and subtracting and summing all those different, basically all based on those 4 values. So back to KNN. How do you really apply it? And again, I've also made a movie of this. So basically you import the classifier, you make an instance of the model, in this case with n as neighbors 1, you fit it, basically this is where you train it, and then you can do prediction. Well, in a previous video Johan explained already that really making the model is quite simple. Well, here you see that in 4 lines of code you can already make a model, which is quite powerful. If we want to see those confusion matrix, classification reports, etc., we can import these and we can compare our results with what we did predict. And then we get all those nice values, which is quite nice that Python and sklearn can give this automatically. We don't have to calculate it by hand. Okay. Yeah, basically these are the same steps as we told you already before. And the key is to find the best classifier and parameters. In case of the KNN, it's the KNN1 or KNN3 or 5, etc. So basically you see here it's always the same form. It's import the classifier, you've got the classifier, there's some options which you can put in. It's always the same set. Tuning. We can manually tune values. This is an example where we manually look at the different values. So what we do is we've got a loop and we've got a list which we're going to populate with the different errors of the different models. Well, not really models, of the different setting of the values. So here we've got a model, classifier, and we're gonna we're gonna loop the I. So each time we train the model, we look at the performance and we put this in this list. With this we just can see what is the performance for the different parameters. It's a little bit trial and error, right? But that's very normal actually. So We just try and see if it works or not. So this is an example for a data set with KNN, and then you can see the impact of different KNN. This training you do with the validation set, right? You're gonna, it's here called X-test, but basically you're gonna use it with the validation set. And then you can fine tune your parameters. So in this case, these would be, well, preferred, I think. You can also see that it's not always logical, right? It's not like a smooth line. It could be a little bit strange. And also that is normal. This thing can also be done automatically. So you can also let Python optimize everything. An example is grid search CV, and then you basically can define a parameter grid. So in this case we're going to do the n neighbors, and we're going to list it from 1 to 40 with a step of 2. And then we're just gonna try this model, this classifier, with this parameter grid, and we're just gonna train it. And then it gives what is the best automatic outcome, which is pretty cool. And by the way, cross-validation is used automatically in this algorithm. Well, we're almost at the end of the first or the movie about KNN. So some pros and cons of KNN. It's very simple. It's very simple. So there's no higher math involved. It's really intuitively understandable. It's easy. Training is easy. It works well with more classes. It's easy to add data later on. It's few parameters to tune. Basically, you've got the KNN, the K parameter, and you've got to choose what kind of a distance matrix. And well, it's a little bit difficult if you've got like 700 or 800 features. But if it's not that many features, you can even visually really see why it choose the prediction which it chooses. There's also some cons. It requires a lot of computations, and all the training data needs to be kept basically in the memory. It's not that it uses really all the time. For each prediction it uses all the training data. And it can have worse performance if data has more features and dimensions. And it doesn't work that well, and that's got a little bit to do with the scaling if you've got categorical features. So they take only a limited number of possible values. Okay, I hope this is a little bit useful for you, and let's continue to the next algorithm.